So now let's work the opposite way. We have a matrix equation. We want to convert it into scalar form. So we want to have x equals equation, y equals equation. So the first thing we're going to do is to bring this into scalar form, we're going to combine all of this stuff into one vector. So scaling 1 and negative 2 by 2e to the 6t will give me 2e to the 6t and negative 4e to the 6t. And then I'll scale 0 by negative 3e to the 2t, which is just going to be plus 0 up here. And negative 3e to the 2t times 2 will give me negative 6e to the 2t. And now I can add these two vectors. So 2e to the 6t plus 0 is just 2e to the 6t. Negative 4e to the 6t minus e to the 2t has to stay like that because I don't have e to the 2t and e to the 6t are not like terms. And so now I can see that x is equal to the top component because the top component needs to equal the top component in the vector. So x is going to equal 2e to the 6t. Y is going to equal negative 4e to the 6t minus 6e to the 2t. And there we have written our answer in scalar form. So now that we know how to work forward and backward, let's look at something that looks at first a little more complex. Define v1 to be the vector 1, 1, v2 to be the vector 2, 1/2. Lambda 1, this is a Greek symbol called lambda. We'll see this arise kind of often. This is lambda. And lambda 1 equals negative 2. Lambda 2 equals 3. The vector x equals just these two scalar components, x and y. k1 equals 5, k2 equals 7. Write the equation vector x equals k1 e to the lambda t I forget this v1 in here, so I just put this in, times v1 plus k2 e to the lambda 2t v2. You will see this quite often, this expression here. So to write x equals k1 e to the lambda 1t v1 plus k2 e to the lambda 2t v2. At first it looks kind of scary, a little bit intimidating. All I'm going to do here is just replace the components with what they are. So the vector x contains x and y in it. k1 is given to us as 5, so 5e to the lambda 1, which is negative 2t. v1 is the vector that contains 1, 1 in it, plus k2, which is 7, e to the lambda 2t, which is 3t. v2 is the vector 2, 1/2. And so now we need to continue to expand this out. So really the purpose of this problem is just to show that we can express it in this, we can express a matrix equation written in this symbolic form, and then we can convert it into actual components. So like before, we're going to distribute the 5e to the negative 2t and the 7e to the 3t. So this will come out to give us 1 times 5e to the 2t, and then 1 times 5e to the 2t again, plus, and then here we'll have 14e to the 3t, and 1/2 of 7, I'll just go ahead and write it as 3.5e to the 3t. And now we add these together, giving us 5e to the 2t plus 14e to the 3t equals x. So the x component is going to be the sum of those, and the y component is going to be the sum of those. And so x will be 5e to the 2t plus 14e to the 3t, and y is going to be 5e to the 2t plus 3.5e to the 3t. And there's our scalar form of that vector, that matrix equation. Another thing we can do with vectors is we can take derivatives and integrals. This might sound scary, but really whenever we perform calculus on vectors, the derivative of a vector is just the derivative of the components. So if we had x and y in here, we take the derivative of x with respect to t, the derivative of y with respect to t, and also the integral of a vector would be the integral of the component and the integral of the other component. So just as a quick example here, find the derivative of this. So the derivative of t squared sine of t is just going to be the derivative of t squared. The derivative of t squared, which we know is 2t, of t squared. And then down here we'll have the derivative of sine of t, which we know is cosine of t. So we'll have the vector 2t cosine t. Simple as that. Now, integral, the integral of this vector will be the integral of the vector t squared sine of t will be, with respect to t, will be the integral of t squared with respect to t, and the integral of sine of t with respect to t. And of course, the integral of t squared is 1/3 t cubed, and the integral of sine of t is negative cosine of t. So that's how we can perform calculus on vectors. That's pretty much all the algebra we're going to be doing on vectors for now, and that's why we call this a crash course. There's a lot of details that we're omitting, but we really just care about having enough to be able to move forward with solving systems of differential equations. So let's take a look at the geometric meaning of multiplying a matrix by a vector. When we multiply a matrix by a vector, we transform it. And transform means just that. You physically change it in some way. Now, in terms of how a vector can change in, say, two-dimensional space or even three-dimensional space, is it can get scaled, so it can get stretched, or it can get, if that's my original vector, then you can get scaled, but it could also get rotated. So maybe what happens to that vector when it gets multiplied by a matrix is it gets rotated and maybe scaled. So here we have a matrix A, and the matrix multiplication that we defined above works here. Just we have a coefficient matrix, and this vector just has numerical components instead of having symbols in it. So what we want to do here is find A times x and plot both the new vector and the original vector. So that being said, let's go ahead and start our plot here, since we already have one of the vectors. And so here we'll just say that, we'll kind of scale this. We'll say here's the 1, 1 vector right there. There's our original x. And then now I'm going to perform the multiplication of A by x and see in what way that's going to transform x. So to do that, I have to take 1, 2, 3, negative 1 and multiply it by the 1, 1 vector. So we know from our past experience that this vector and this vector are going to get scaled by this and this respectively, and the results are going to get added together. So we'll have 1 times the 1, 3 vector plus 1 times the 2, negative 1 vector, and really I'm just adding across here because the scalars are 1. So 1 plus 2 and 3 minus 1. So you can see here that now this new vector is at the location 3, 2, which we can see that both of those effects have taken place, that we have both scaled and we have rotated the vector. So 1, 1, that has a length of the square root of 1 squared plus 1 squared, which is the square root of 2, but this guy, the square root of 9 plus 4, this guy has a length of the square root of 13, so that green vector is a little bit longer. So we have a scale and a rotation. Now in a linear algebra class, you talk about different types of transformations and how do you rotate a certain number of degrees or a certain number of radians, and how do you get a matrix to scale your vector for you in a very specific way, but we don't need to get into that here.